For more than a century, we have been quietly assembling a picture of reality, a remarkably precise picture. We call it the Standard Model. It is, by every conventional measure, a triumph. It explains how atoms bind together, how stars ignite and burn for billions of years, how invisible forces sculpt galaxies and keep our feet firmly planted on the ground. It is the most rigorously tested framework in the history of science. Again and again, experiments confirm its predictions. Again and again, the equations hold. According to this picture, the universe is orderly, uniform, predictable, safe. There is only one problem. The universe itself does not seem to agree. When we turn our telescopes toward the sky, when we stop trusting the equations and start listening to the data, we encounter things that simply should not exist. Structures that are too vast to have formed so quickly. Matter moving faster than gravity allows. Energy appearing where nothing should be. It is like discovering a locked room in a house you built with your own hands. Every blueprint accounted for, every measurement verified. And yet, the door is there. These are not small discrepancies, not rounding errors, not technical noise. They are bright red warning signs, signals that our understanding of reality may be incomplete. Or worse, fundamentally wrong. We are observing objects that seem older than the universe itself, detecting signals emerging from what should be empty space, measuring constants of nature that may not be constant at all. So, today, we are going to look directly at the evidence. All of it, from strange cold regions in the oldest light ever observed, to missing matter in our own cosmic neighborhood. We will explore 50 ways the universe is defying our expectations. Because right now, something is very wrong, and the deeper we look, the stranger it becomes. Let's begin with the map. If you observe the cosmic microwave background, the faint afterglow of the Big Bang, it should resemble static on an old television. Tiny temperature fluctuations, scattered randomly across the sky. This expectation comes from the cosmological principle, the idea that the universe is the same in every direction. No preferred locations, no hidden patterns, no special vantage points. And for a long time, that assumption seemed safe. Then we found the cold spot, first detected by the WMAP satellite, and later confirmed by the Planck mission. This anomaly sits in the southern hemisphere of the sky, a vast region that is simply wrong. It is colder than it should be. Between 70 and 150 microkelvin colder than the surrounding universe. That may sound insignificant, but in cosmology, that difference is enormous. It is the difference between a ripple and a tsunami. Statistically, a cold region this large and this extreme has less than a 1% chance of appearing by accident under the Standard Model. It stands out like a dark bruise on an otherwise flawless apple. Naturally, scientists assumed there must be a mistake. They checked the instruments. They accounted for dust and foreground interference. They scrutinized the data again and again. But the cold spot remained. It is real, and it is enormous. So if it is not an error, what is it? The most conservative explanation is a supervoid. Imagine an immense region of space, nearly 8 billion light-years across, in the direction of the constellation Eridanus. A place with far fewer galaxies, fewer stars, less matter than normal. A vast cosmic emptiness. As light from the cosmic microwave background passes through this region, it experiences weaker gravitational pull. It loses energy as it climbs back out. This process is known as the integrated Sachs-Wolf effect. Less energy means colder light. Case closed. Except, it isn't. We did find a void in that direction. The Eridanus supervoid, the largest void ever mapped. But it is not empty enough. Even a structure of that scale can only account for 10 to 20% of the temperature drop we observe. The numbers refuse to cooperate. It is like trying to explain a shattered window with a single pebble. So the question remains, what caused the rest of the cold? And this is where the discussion becomes uncomfortable. Because the next explanation sounds less like cosmology and more like science fiction. What if the cold spot did not originate in our universe at all? Some theoretical physicists, including Laura Mersini-Houghton, have proposed a radical possibility. Our universe may be just one bubble in a vast cosmic foam, a multiverse. In the earliest moments after the Big Bang, during the universe's violent inflationary expansion, our bubble may have collided with another. If two universes brushed against each other, the impact would leave a scar, a region where matter was displaced, where energy was altered, a cold spot. To be clear, this is not the mainstream view. It is speculative, highly controversial. But the fact that serious scientists are willing to consider it tells us something important. This anomaly is so stubborn, so resistant to conventional explanation, that it forces us to question the boundaries of reality itself. We may be staring at a patch of sky that does not belong entirely to our universe. As unsettling as that idea may be, it is only the beginning, because the cold spot is not the only place where the universe refuses to behave. There is something else hidden in the cosmic background, something even harder to ignore. Cosmologists call it the axis of evil. And no, that name is not a joke. Remember, the universe is supposed to have no preferred direction, no cosmic up or down. Yet when researchers analyzed the largest scale temperature patterns in the cosmic microwave background, they found something disturbing. The hot and cold regions appear aligned, not randomly scattered, but arranged along a specific axis. And the most unsettling part, that axis aligns almost perfectly with the plane of our own solar system. Think about what that implies. This radiation comes from 13 billion years ago, long before Earth existed, long before the Sun ignited. It should not care where our planets orbit. And yet, the data suggests the universe itself is somehow oriented with us. Copernicus spent his life showing that Earth is not the center of the cosmos. The axis of evil seems to whisper that maybe we are special after all, or far more likely, that our understanding of the universe's structure is deeply incomplete. Perhaps space has a strange topology, a twisted geometry, a shape that forces alignments we do not yet comprehend. Either way, the map is not random. It has direction, and we do not know why. And while we are examining motions that should not exist, let's talk about traffic. In an expanding universe, everything should be moving away from everything else, like dots on the surface of an inflating balloon. At large enough scales, expansion should dominate all motion. But in 2008, a team led by Alexander Kashlinsky found something profoundly unexpected. They examined hundreds of galaxy clusters and discovered they were not just expanding, they were drifting. A vast river of galaxies stretching across billions of light years, flowing together in the same direction at nearly 2 million miles per hour. And no known force in our model can explain why. They named this phenomenon dark flow. It is motion that does not obey the expansion of space itself. It runs sideways to the cosmic stretching, indifferent to the rules that govern everything else. Imagine tossing corks into a lake as it explodes outward and watching them all drift together in the same direction. Not outward, but across the blast. That drift points toward a specific region of sky, between the constellations Centaurus and Hydra. And whatever is pulling on these galaxy clusters must be enormous, far larger than anything we can see within the observable universe. Yet there is nothing there. No visible anchor, no luminous titan. The flow simply goes. Part of this motion has a familiar suspect, a local gravitational behemoth known as the Great Attractor. It lies roughly 250 million light-years away, hidden behind the dense dust lanes of our own Milky Way. In a region astronomers call the zone of avoidance, optical telescopes cannot pierce it, but gravity does not need light. Our galaxy, along with everything nearby, is being pulled toward that region at nearly 600 kilometers per second. X-ray surveys have revealed massive galaxy clusters there, including the Norma cluster, confirming that something huge is hiding behind the veil. But when astronomers add up all the mass they can see, it still isn't enough. At best, it accounts for about half of the gravitational pull. The rest is missing. We feel the tug. But when we look into the darkness, there is only shadow. It's like holding a fishing line drawn tight, knowing something powerful is pulling back, but seeing nothing beneath the surface of the water. And then the picture grows even stranger. When scientists looked beyond the great attractor, they realized it was not the boulder after all. It was a pebble. Behind it looms the Shapley supercluster, located about 650 million light-years away. Shapley is the most massive concentration of galaxies in our local universe, more than 8,000 galaxies, with a combined mass equivalent to 10 million billion suns, and we are falling toward it. But even Shapley is not standing still. As maps improved, a larger truth emerged: the Milky Way, the Virgo cluster, the Great Attractor, and Shapley are all parts of something far grander. A vast gravitational basin called Laniakea, a supercluster shaped like luminous tendrils, flowing inward toward a central valley of mass. The name means immeasurable heaven in Hawaiian, and it fits. We are not at the center of anything. We are a grain of dust sliding slowly down one slope of an unimaginably large gravitational landscape. But even Laniakea is moving. The dark flow does not stop there. It suggests that something even larger, something beyond the edge of our observable map, is tugging on the entire cosmic web. We are small fish in a very, very large current, which brings us to a problem of scale. Cosmologists have a rule known as the end of greatness. It states that beyond roughly 1-2 billion light-years, the universe should smooth out, zoom out far enough, and structure should dissolve into uniformity. Gravity simply hasn't had enough time since the Big Bang to build anything larger. That's the rule. But gravity, it seems, never received the memo. In 2021, astronomers identified a structure now known as the Giant Arc, a crescent-shaped arrangement of galaxies stretching an astonishing 3 billion light-years across the sky, nearly 3 times larger than the theoretical limit. This is not a rounding error. It is a violation. Finding the Giant Arc is like discovering a human femur 30 feet long. Biology says it shouldn't exist. Cosmology says this structure should not exist. Yet there it is, etched unmistakably into the data from the Sloan Digital Sky Survey. If structures this large can form, then the cosmological principle itself is in trouble. The universe may not be uniform at the largest scales. The map isn't just fuzzy. It may be fundamentally wrong. And sometimes the problem is not size but shape. Galaxies usually come in familiar forms. Spirals, like our own Milky Way, or ellipticals, featureless, swollen blobs, messy, asymmetrical, forged through collisions and chaos. Then there is Hoag's object, a perfect ring of blue stars encircling a lonely, golden core. No bridges, no spokes, no visible connection between them. Just a ring and a center floating in pristine isolation. Hoag's object sits about 600 million light-years away, and it looks less like a galaxy and more like something carefully designed. The standard explanation for ring galaxies requires a collision, one galaxy plunging straight through another. But collisions leave scars, debris, tidal tails. Hoag's object is clean, too clean. There is no sign of the intruder that should have created it. No wreckage, no smoking gun. Our simulations struggle to reproduce it. Either it is a 1 in a billion cosmic fluke, or it is evidence that there are ways to build galaxies we do not yet understand. And if this were a single oddity, we might shrug and move on. But the strangeness does not stay isolated. It spreads. This is exactly what we see with quasars. Quasars are the blazing cores of distant galaxies, powered by supermassive black holes devouring matter at furious rates. They launch jets of energy across millions of light-years. Because galaxies are separated by vast distances, their orientations should be random. A black hole on one side of the universe should have no knowledge of one on the other. They have never met. They cannot communicate. Gravity is far too weak to link them across such scales. And yet, in 2014, observations from the Very Large Telescope revealed something deeply unsettling. Quasars separated by billions of light-years are aligned. Their rotation axes run parallel to one another. Not a few, not locally, but across enormous stretches of space. This is coordination without contact, structure without communication. It suggests an invisible framework, perhaps colossal filaments of dark matter we cannot see, or perhaps a fossil imprint from the very moment of creation, when everything was once connected, and the universe retained a memory of that contact. Either way, we are forced toward an uncomfortable conclusion. The universe is not a collection of isolated islands. It is a web, and the threads holding it together are invisible. We are watching a cosmic puppet show, but we cannot see the strings. And if we cannot see the strings, do we truly understand what or who is pulling them? To see how deep this problem goes, we have to rewind further than structure, further than motion, back to the origin story itself, to the history of everything. Before December 25, unsettling archives, before the launch of the James Webb Space Telescope, cosmology had a story it felt comfortable telling. A clean timeline, orderly, predictable. After the Big Bang, the universe entered a dark age, a vast ocean of neutral hydrogen. No stars, no galaxies, no light. Then gravity went to work. Slowly, painfully, tiny clumps formed first week. Chaotic protogalaxies, over billions of years. These fragments merged and grew through a process called hierarchical clustering. Small things became big things. Eventually, that story was written into every textbook, encoded in every simulation. Then James Webb opened its golden eye, looking deeper into the infrared than any telescope before it. Webb peered back to when the universe was only 300 to 500 million years old, redshift 10 and beyond. According to the model, this era should have been messy and primitive, cosmic toddlers stacking blocks. Instead, Webb found giants, bright, massive, structured, galaxies with defined disks, some even showing spiral features. Not infants, adults. One object in particular, GZ9P3, appeared far too massive for its age. There simply had not been enough time. Gravity needs time. Cooling needs time. Rotation needs time. Yet these galaxies had already done it all. It was like planting an acorn and returning an hour later to find 100-foot oak. Roots deep, branches full. Biology says that cannot happen. Physics says these galaxies cannot exist. And yet they do. They are there watching us from the dawn of time, quietly dismantling the timeline we thought we understood. The numbers were so extreme that, at first, many astronomers assumed something had gone wrong. Maybe the telescope was miscalibrated. Maybe the models translating light into mass were flawed. Maybe this was all an illusion created by dust, noise, or an overlooked artifact. So they checked. And then they checked again. The calibration held. The signal remained. And slowly, uncomfortably, the conclusion set in. The early universe did not ease itself into structure. It exploded into it. To understand how deep this problem runs, you have to stop thinking in metaphors and look directly at the numbers. In February 2023, a team led by astronomer Ivo Labe at Swinburne University of Technology published a paper in Nature that sent shockwaves through astrophysics. Using early James Webb data, they identified 6 candidate galaxies dating from just 500 to 700 million years after the Big Bang. These were not slightly oversized. They were impossibly massive. By analyzing their light, how bright it was, how redshifted, how evolved, the team estimated their stellar mass. The total amount of material already locked up in stars. Some of these galaxies appeared to contain 10 billion to 100 billion times the mass of the Sun. One object in particular, catalogued as 1 miljoner 514, stood out. Its estimated stellar mass rivaled that of the modern Milky Way. Let that sink in. Our galaxy took 13 billion years, countless mergers, and an endless diet of smaller galaxies to reach its current size. These early galaxies did it in less than 5% of that time. This is where the mathematics collapses. In cosmology, we know the baryon budget of the universe. Baryons are normal matter, protons and neutrons, the stuff that makes stars, planets, and people. The ratio of normal matter to dark matter in the early universe is well measured. It is not flexible. You cannot magically create extra gas. Yet, if these mass estimates are correct, these galaxies would have had to convert nearly 100% of the available gas in their dark matter halos directly into stars. With perfect efficiency, that never happens. Star formation is violent and wasteful. As stars ignite, they blast out radiation, stellar winds, and eventually supernova explosions that blow remaining gas away. This process, called feedback, chokes off further growth. In the real universe, galaxies are lucky to convert 10 to 20% of their gas into stars. For Labi's galaxies to exist, they would need to eat faster than the laws of physics allow. They are, quite literally, too heavy for their time. Either our mass estimates are catastrophically wrong, perhaps contaminated by hidden black holes or unusual stellar populations, or our understanding of how galaxies form is deeply flawed. And if it's the latter, then the standard model isn't missing a detail, it is wrong at the very beginning. If galaxies were growing this fast, then whatever sits at their centers is even more disturbing. Because at the heart of galaxies lie supermassive black holes. In the present-day universe, these objects grow slowly, over billions of years. By swallowing gas and merging with other black holes, the one in our own galaxy, Sagittarius A times, weighs about 4 million solar masses. That already took a long time. But in the early universe, we are finding black holes that are absurdly large, far too soon. Consider quasar J300, 13.806. Discovered in 2021, we see it as it existed just 670 million years after the Big Bang. At its core sits a black hole with a mass of 1.6 billion suns. That number is devastating. There is a hard speed limit on how fast black holes can grow, known as the Eddington limit. As matter falls in, it heats up and shines. That light pushes outward, creating radiation pressure that fights gravity. If a black hole feeds too fast, its own brightness pushes the fuel away. It's like trying to drink from a fire hose, the pressure knocks you backward. If you start with a normal black hole seed, say, the remnant of a massive star, 10 or 20 solar masses, and let it eat continuously at the Eddington limit, it would take nearly 1 billion years to grow to the size we see in J313. But the universe simply wasn't old enough, even under unrealistically perfect conditions. The math does not work. So either the Eddington limit can be broken, requiring exotic, untested physics, or these black holes did not start as stars. They started as something else, something massive, something that skipped the entire childhood phase. And that possibility unsettles physicists, because it implies a violent mechanism in the early universe we have never directly observed. This leads us to one of the most extreme ideas in modern cosmology: direct collapse. Black holes. Normally, black holes are born from stars. Stars live, burn, exhaust their fuel, and collapse. But the direct collapse theory proposes a shortcut. Imagine a colossal cloud of pristine gas, hydrogen and helium, only millions of times the mass of the Sun, drifting in the early universe. Under normal conditions, that cloud would cool, fragment, and break into thousands of stars. Cooling leads to fragmentation. That is basic physics. But what if the gas could not cool? If intense ultraviolet radiation from a nearby galaxy destroyed the molecules needed for cooling? the cloud would stay hot. And hot gas does not fragment. Instead, gravity would pull the entire cloud inward as a single object. No stars, no fusion, no resistance, just collapse. The cloud would shrink, grow denser, and eventually snap, punch a hole in space-time itself. Instead of a black hole weighing tens of solar masses, you would instantly get one weighing 10, null, 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 or even 100. 000 suns. A heavy seed. From there, growth becomes easy. Mergers and accretion could build a billion solar mass monster quickly enough to match what James Webb is seeing. It sounds elegant, but it comes at a cost. The conditions required pristine gas plus just the right amount of nearby radiation are extraordinarily rare. Simulations suggest they shouldn't occur often enough to explain all the early supermassive black holes we observe. And yet, those black holes exist, which means the universe found a cheat code. It built giants before it built stars. The early cosmos was not a quiet nursery. It was a factory collapsing entire clouds of potential stars directly into darkness. While we're questioning timelines, let's look at something much smaller but just as revealing. Dust. Cosmic dust may sound mundane. Tiny grains of carbon, silicon, aluminum. But dust is a cosmic clock. The Big Bang did not make dust. It produced hydrogen, helium, and a trace of lithium. All heavier elements, what astronomers call metals, are forged inside stars. Stars must be born, live, and die, often in violent supernova explosions, to scatter those elements into space. Then the dust has to cool, survive shock waves, and clump together. It's a multi-generational process. You need stellar grandmothers. So, when astronomers looked at galaxy A 2744 YD4, located 2 billion light-years away, meaning we see it just 600 million years after the Big Bang, expectations were clear. It should have been clean, primitive, almost dust-free. But it wasn't. When the ALMA telescope in Chile observed it, it detected the thermal glow of dust 6 million solar masses worth. This is like finding a crime scene where the body appears before the weapon was ever invented. Even if the first stars, so-called population 3 stars, were massive and short-lived, it's incredibly difficult to explain how they could create this much dust so quickly. Worse still, supernova explosions tend to destroy dust with their shock waves, shattering grains almost as fast as they form them. So the dust shouldn't survive. Yet there it is. Some theories suggest quasars might help manufacture dust. Others propose that dust grains grow much faster in the interstellar medium than we thought. But none of these explanations fully match the data. The unavoidable implication is this: the early universe was chemically mature far earlier than it should have been. We are staring at a cosmic teenager with grey hair and wrinkles. The birth certificate does not match the face. And if dust in the infant universe is unsettling, what comes next is even harder to swallow. Imagine meeting someone who calmly insists they are older than their own mother. It sounds absurd. Biology doesn't allow it. Cause must come before effect. Parents must exist before children. Time only moves one way. And yet, in astronomy, we are confronted with a star that appears to do exactly that. Its catalogue name is HD Cent 40283, but it is far better known as the Methuselah star. It lies just 200 light-years from Earth. In the constellation Libra, it streaks through the Milky Way at an unusually high speed, a clue that it does not belong here. Astronomers believe it was born in a small dwarf galaxy that was torn apart and absorbed by the Milky Way billions of years ago. Its motion tells a story of ancient violence and long exile. But its motion is not what unsettles scientists. Its age is. For more than a century, astronomers have studied Methuselah's light in extraordinary detail. By measuring its chemical composition, especially how little iron it contains, we can estimate when it formed. Iron is forged in generations of stars, The earliest stars formed before the universe was polluted with heavy elements. Less iron means greater age, and Methuselah has almost no iron at all. It is nearly pure hydrogen and helium. In 2013, using precision data from the Hubble Space Telescope, scientists calculated its age 14, 5 billion years. Pause there. The age of the universe itself, based on measurements from the Planck satellite, is Kolmetoista, 8 billion years. So how can a star be older than the universe? It is the ultimate chronological paradox, like discovering a Roman coin dated 500 BC embedded inside a dinosaur fossil. It should not exist. Astronomers immediately went into damage control mode. They refined stellar evolution models. They adjusted oxygen abundances. They widened the error bars with extreme assumptions. They managed to pull Methuselah's age down to about 14, 3 billion years, with an uncertainty of roughly 800 million years. If you stretch everything to the absolute limits, making the universe as old as possible and the star as young as possible, the numbers just barely overlap. Barely. It is an uncomfortable squeeze. A statistical balancing act performed at the edge of impossibility, and the fact that nature allows a star to sit precisely on that knife edge suggests something deeper. Either our models of stellar evolution are subtly wrong, or the universe itself is older than we think. And age inconsistencies don't stop with stars. They show up in the ingredients of the universe itself. Let's talk about lithium. Cosmologists possess one of the most precise recipes ever written: Big Bang nucleosynthesis. It tells us exactly how much hydrogen, helium, and lithium should have formed in the first few minutes after the Big Bang. For hydrogen and helium, the recipe works beautifully. Observations match predictions almost perfectly. It is one of the great triumphs of modern physics. But lithium ruins everything. According to theory, early stars should contain a specific baseline amount of lithium-7. Astronomers measure this using what's called the Spite Plateau, a remarkably consistent lithium level observed in ancient stars. And the result is shocking. We see only about 1/3 of the lithium the Big Bang predicts. 2/3 is missing. This is not a rounding error. It is a discrepancy of 300–400%. So where did it go? We checked the telescopes. The spectral lines are clean. We modeled stellar interiors. Stars do burn lithium, but nowhere near enough to explain the deficit, which leaves an unsettling possibility: new physics. Some physicists suggest that unknown particles, such as axions or decaying dark matter, may have interfered with nuclear reactions in the first moments of time, destroying lithium before it could survive. If that's true, the lithium problem isn't just missing atoms. It's a fossil record of a particle we haven't discovered yet, and the universe's ingredient list remains incomplete. If missing elements feel abstract, let's make the problem bigger. Let's talk about missing galaxies. Our standard cosmological model relies on cold dark matter, an invisible substance that provides the gravitational scaffolding for galaxies. Massive computer simulations, like the Millennium simulation, predict that galaxies like the Milky Way should be surrounded by hundreds or even thousands of small dark matter clumps. Each clump should host a tiny satellite galaxy. The Milky Way should be swarming with them. So astronomers went out to count. They found about 50. The simulations say thousands. The sky says 50. This is the missing satellites problem, a major embarrassment for the cold dark matter model. Where are the rest? Perhaps they exist but are invisible dark galaxies, clumps of dark matter that never formed stars. If so, our galaxy may be surrounded by thousands of silent, unseen neighbors drifting through us like ghosts. Or perhaps dark matter isn't cold at all. Maybe it's warm, faster-moving particles that smooth out small structures, preventing tiny galaxies from forming in the first place. That would fix the satellite count, but it breaks other things, like the detailed structure of the cosmic web. Every solution fixes one problem by creating another. So is the Milky Way lonely or haunted? Another chapter of cosmic history is missing key pages. It's called the epoch of reionization. After the Big Bang, the universe cooled and filled with neutral hydrogen gas, a thick, light-blocking fog. For hundreds of millions of years, the universe was effectively dark. Then something turned the lights on. The first stars and quasars emitted ultraviolet radiation, stripping electrons from hydrogen atoms and clearing the fog. This made the universe transparent, allowing light to travel freely across cosmic distances. We know this happened, but when we try to balance the energy budget, the numbers fail. Observations of distant quasars through features like the Gunn-Peterson Trough suggest reionization ended around 1 billion years after the Big Bang. Yet when astronomers count all known galaxies and quasars from that era, they don't produce enough ultraviolet light. You need X photons. The universe supplies Y, and Y is far smaller than X. So what cleared the fog? A hidden population of massive stars that vanished without trace. Black holes radiating far more efficiently than we think. Exotic energy sources like decaying dark matter. We see a transparent universe, but we cannot find the switch that turned the lights on. Now, let's combine mysteries. What if the missing dark matter and the early black holes are the same thing? This brings us to primordial black holes. In the 1970 seconds, Stephen Hawking proposed that during the chaotic, high-density moments, just after the Big Bang, long before stars existed, some regions of space may have collapsed directly into black holes. Not stellar black holes, primordial ones. They could be microscopic, with the mass of a mountain packed into a proton-sized object. Or they could be enormous thousands of solar masses. If they exist, they solve multiple problems at once. Why did massive black holes appear so early? Because they were born that way. Where is the dark matter? Maybe it isn't a particle at all. Maybe it's billions of ancient black holes drifting invisibly through space. Elegant, terrifying, because if dark matter is made of primordial black holes, the universe is a minefield. Right now, an invisible black hole could be passing through our solar system. A small one would punch through Earth like a bullet, causing seismic shock. A larger one could destabilize planetary orbits. We've searched for them. We've looked for evaporation flashes. We've watched stars for gravitational lensing. No smoking gun yet. But LIGO has detected black hole mergers with masses that fit primordial predictions better than stellar ones. The question hangs unresolved. Are we surrounded by ancient traps left over from creation? When you put all of this together, impossibly old stars, missing lithium, galaxies that grew too fast, it points toward one terrifying possibility. Our cosmic clock may be wrong. The age of the universe, 8 billion years, is the foundation of modern cosmology. It comes from the expansion rate, the Hubble constant, and assumptions about dark energy. But if stars seem older than the universe, maybe the universe itself is older. In July 2023, physicist Rajendra Gupta from the University of Ottawa published a controversial paper suggesting the universe could be 7 billion years old, nearly double the accepted age. He combined two radical ideas: tired light, an old theory where photons lose energy simply by traveling long distances, and evolving physical constants, where values like gravity or the speed of light change over time. If Gupta is right, the impossible galaxies seen by James Webb suddenly make sense. They had twice as much time to grow. The Methuselah star fits comfortably. The timeline relaxes, but the cost is enormous. It breaks, Big Bang, nucleosynthesis. It disrupts the cosmic microwave background, and tired light has long been disfavored because it blurs distant images which we do not observe. Most astronomers remain unconvinced, but the fact that such a radical proposal appeared in monthly notices of the Royal Astronomical Society says everything about the situation. We are so boxed in by the data that rewriting the age of the universe is now on the table. If the timeline is broken, what about our neighbors, or the lack of them? This leads us to the Fermi Paradox. with 200 billion stars in the Milky Way, many with planets, some inhabitable zones. We should see signs of life. But when we listen, we hear nothing. The great silence. In astronomy, silence is not comforting. It's alarming. It's like walking into Times Square at noon and finding it completely empty. Something is wrong with our assumptions. Are civilizations self-destructive? Is there a great filter that wipes them out before they spread? Is it behind us or still ahead? If it's ahead, the silence isn't empty. It's a graveyard. Except, the universe did scream once. In 1977, at the Big Ear Radio Telescope in Ohio, astronomer Jerry Amon detected a powerful radio spike at 1,420 megahertzes, the frequency of hydrogen. It lasted 72 seconds, exactly matching Earth's rotation. It was 30 times stronger than background noise. Narrowband. Clean. Amon circled it and wrote one word: wow. We never heard it again. Comet, satellite, unknown, natural source, nothing fits perfectly. The phone rang once, and the caller hung up. Then there are fast radio bursts, millisecond-long blasts, releasing the energy of the sun over days. Some repeat. Some cycle with eerie regularity. FRB 121102 fires unpredictably from 3 billion light-years away. FRB 180916 pulses on a strict 16-day cycle. Nature rarely keeps schedules. Some scientists cautiously suggest artificial origins, planet-scale engines, light sails, unknown technologies. Others insist on exotic neutron stars. Either way, the universe is far more violent, active, and mysterious than we ever imagined. And if you want something that looks even more like an alien engine, then you need to look at Ki 8462852. As Oumuamua began its exit from the solar system, something happened that forced astronomers to sit up straight. It accelerated, not because of gravity, not because of a planetary slingshot, but as if something were pushing it. Comets accelerate all the time. When they approach the sun, their ices heat up, sublimate, and vent gas like tiny thrusters. That outgassing creates a measurable push. But Oumuamua showed no coma, no tail, no visible plume of gas or dust. Even the most sensitive telescopes saw nothing. And yet the acceleration was real. It followed an inverse square law, perfectly aligned with solar radiation pressure, as if sunlight itself were pushing the object away. That immediately suggested something extraordinary, because for sunlight to push an object that much, the object must be extremely thin, paper thin. In 2018, Harvard astronomer Avi Loeb and his colleague Shmuel Bialy published a paper proposing an explanation that detonated across the scientific world. What if Oumuamua was not a rock at all? What if it was a light sail, a thin, flat structure, perhaps only a fraction of a millimeter thick, would experience enough radiation pressure from sunlight to account for the observed acceleration? The math worked disturbingly well. Too well. Loeb was careful. He didn't say it was alien technology. He said it was consistent with technology. And that alone was enough to ignite a firestorm. Critics pushed back hard. They proposed exotic natural explanations. Maybe it was made of hydrogen ice, sublimating invisibly. But hydrogen ice evaporates too quickly to survive interstellar travel. Maybe nitrogen ice, chipped off a Pluto-like world. But that would require a population of nitrogen-rich planets far larger than anything we observe. Every explanation felt strained. Oumuamua didn't just fail to fit one box. It didn't fit any box. It was the first known interstellar object ever detected passing through our solar system. And instead of easing our curiosity, it deepened it. It didn't look like a comet. It didn't behave like an asteroid. And it didn't act like anything we've seen before. Was it debris from another star system, a fragment of an exotic world, or something else entirely? What made it worse was timing. We didn't see it coming. We only noticed Oumuamua after it had already passed its closest approach to the sun. By the time we realized what it was already leaving, slipping back into the dark between the stars. A messenger arrived and left before we could ask questions. Since then, astronomers have spotted a second interstellar visitor, Dvi Borisov, in 2019. But Borisov behaved exactly like a comet should. It outgassed. It formed a tail. It made sense. Oumuamua did not. And that matters, because if interstellar space occasionally sends us visitors, then Oumuamua may not be unique. It may simply be the first one we noticed, which raises a deeply unsettling possibility. What if the universe is not silent because nothing is out there, but because we haven't been listening the right way? Throughout this journey from cold spots in the cosmic microwave background, to galaxies that grew up too fast, to stars older than time, to black holes born too large, to dust appearing before its parents, to lithium gone missing, to civilizations that never speak, we keep running into the same wall. Reality does not behave the way our models say it should. The standard model of cosmology is still incredibly successful. It predicts the large-scale structure of the universe with astonishing accuracy. It explains the expansion of space, the formation of galaxies, the relic glow of the Big Bang. But everywhere we look closely, it leaks. The leaks aren't small. They aren't rare. They are piling up. Structures are too large. Objects are too old. Processes happen too fast. Signals appear without sources. Voids are too empty. Alignments are too precise. Silence is too complete. It is as if the universe is running on rules we only partially understand. And every new instrument, every deeper survey pulls back another layer to reveal something unsettling underneath. Maybe the universe is older. Maybe physics changes with time. Maybe dark matter isn't a particle. Maybe intelligence is common but invisible. Maybe we are early. Maybe we are late. Maybe we are lucky. Maybe we are doomed. What is becoming clear is this: the universe is not obligated to make sense to us. For the last century, we have been building a clean, elegant picture of reality, a universe that is uniform, predictable, and safe. A cosmos that began, evolved, and cooled according to equations we could write down and test. But the data is telling a different story. A story of exceptions, of anomalies, of things that shouldn't exist but do. We are not standing on solid ground anymore. We are standing on cracks. And the deeper we look, the more those cracks begin to connect. The greatest danger is not that the universe is strange. It's that we are only just beginning to realize how strange it really is. As with comets, there is a familiar mechanism that can produce small, non-gravitational accelerations. When a comet approaches the sun, heat awakens the ice locked beneath its surface. Gas erupts outward in narrow jets, acting like microscopic rocket engines. That outgassing gently nudges the comet off its purely gravitational path. It's a well-understood effect, observed countless times. But Oumuamua refused to play by those rules. There was no tail, no surrounding cloud of gas, no dusty halo catching sunlight. The Spitzer Space Telescope, designed to detect even faint thermal signatures, searched for warmth that would betray escaping material. It found nothing, absolute silence, and yet the object accelerated anyway. Thence, elongated body shaped like a cigar or a flattened disc was being pushed without any visible propulsion. That contradiction is what pushed Avi Loeb, chair of Harvard's astronomy department, into uncomfortable territory. He proposed a hypothesis that made many scientists uneasy, not because it violated the data, but because it fit it too well. What if Oumuamua was a light sail, a thin structure, possibly millimeters thick, could be pushed by the pressure of sunlight alone? No fuel, no exhaust, just photons transferring momentum. The equations matched the observed acceleration almost perfectly. The backlash was immediate. The community searched desperately for natural explanations. Perhaps it was an iceberg made of hydrogen, sublimating invisibly. But hydrogen ice is extraordinarily difficult to form and would not survive the interstellar journey. Perhaps it was nitrogen ice, torn from a shattered Pluto-like world. But such fragments should be exceedingly rare. Others suggested a porous, fractal dust bunny, lighter than anything we've ever seen. Every proposal patched one hole while opening another. The light sail hypothesis, radical as it sounded, required the fewest assumptions. That didn't make it true, but it made it unsettling. Whether Oumuamua was a rock or a relic, it proved something undeniable. We are not sealed off. Material from other star systems enters ours, and if one object slipped through while we weren't watching, how many passed unnoticed before we even knew to look? It was a wake-up call. The doorbell rang. By the time we reached the door, the visitor was already gone. So let's step back, not from strange objects, but from the rules themselves, because beneath black holes, alien signals, and cosmic anomalies lies a question that disturbs physicists more than any single observation. Why does reality seem so perfectly tuned? This is the problem of fine-tuning. Look at the fundamental constants, the numbers that define how the universe works, and they appear balanced on a knife's edge. Take the strong nuclear force, the glue that holds atomic nuclei together. Increase it by just 2%, and hydrogen would fuse into helium almost instantly after the Big Bang. No hydrogen means no water. No long-lived stars like the Sun. The universe would burn itself out in a flash. Reduce that force by 2%, and protons and neutrons wouldn't bind at all. No atoms. No chemistry. Just a thin soup of particles drifting forever. Now consider the cosmological constant. The strength of dark energy. Its value is absurdly small, 0 point. Then roughly 120 zeros. Then a 1. If it were slightly larger, the universe would have ripped itself apart before galaxies could form. Slightly smaller, and gravity would have crushed everything back into a collapse almost immediately. It's like walking into a room and finding a pencil balanced perfectly on its tip. Possible in theory, ridiculous in practice. This leads to the anthropic principle. We observe these values because if they were different, we wouldn't be here to notice them. It's a selection effect, but as an explanation, it feels hollow, like saying, I won the lottery because otherwise I wouldn't be holding the ticket. It explains survival, not design. And so we are left with two deeply uncomfortable options. Option 1, the multiverse. Countless universes exist, each with random physical constants. Most are sterile, empty, stillborn. We happen to live in one of the rare habitable bubbles, because only such bubbles can host observers. It's an infinite lottery where we drew a winning ticket. Option 2, the universe was set up, whether through simulation, deeper physical laws, or something beyond our current understanding. The dials were turned deliberately. Science recoils from this option because it sounds uncomfortably close to theology. Yet the multiverse demands an infinity of unseen universes just to explain this one. Right now, we cannot tell which game we are playing, an infinite lottery or a rigged table. And just when you think the questions can't get worse, physics itself begins to fracture. The most serious crisis in modern cosmology has a deceptively simple name, the Hubble tension. It asks one question: how fast is the universe expanding? There are two fundamentally different ways to measure this, and they do not agree. The first looks at the early universe. Using data from the Planck satellite, scientists analyze the cosmic microwave background, the afterglow of the Big Bang. They measure the physics of the universe when it was just 380,000 years old. Feed those values into the lambda CDM model and evolve the universe forward in time. The result is clean and precise, 67 kilometers per second per megaparsec. The second method looks at the late universe. It measures distances directly using standard candles like Cepheid variable stars and type Ia supernovae. This is cosmic tape measuring, watching how fast galaxies are moving away from us right now. That result comes back higher, 73 to 74 kilometers per second per megaparsec. The error bars don't overlap. This is a 5 sigma discrepancy, a 1 in 3. 5 to million chance of being a statistical fluke. In physics, 5 sigma means something is broken. At first, scientists blamed the tools. Maybe Planck had calibration issues. It didn't. Other CMB experiments confirmed the number. Maybe the Cepheids were contaminated by nearby stars. Then James Webb remeasured them with unprecedented resolution. The value stayed high. The tension didn't fade. It grew. This means something happened between the early universe and today that our equations don't account for. Maybe dark energy evolved over time. Maybe gravity behaves differently on cosmic scales. Maybe unknown particles influenced expansion. Whatever the answer, the implication is severe. Our most successful model of the universe is missing a crucial gear to untangle the mess. Astronomers tried a new cosmic ruler, the tip of the red giant branch. Red giants reach a predictable maximum brightness before igniting helium, a physical limit rooted in nuclear physics. Cleaner than Cepheids. Simpler. More reliable. If TRGB gave 60 set, the early universe model would win. If it gave 74, the late universe model would win. The answer, 69. Bar. Right down the middle. Now we had 3 numbers, 3 methods, 3 truths that refused to align. The universe wasn't just disagreeing with us, it was contradicting itself. James Webb was supposed to settle the debate. Instead, it sealed it. By confirming the high expansion rate with unmatched precision, Webb made one thing clear. The measurements are not the problem. The theory is, the universe is expanding faster than our mathematics allows. Something is pressing the accelerator, and we don't know what it is. To fix the model, physicists have turned to a last resort idea. It's called early dark energy. We usually think of dark energy as a late-time phenomenon, turning on about 5 billion years ago to drive accelerated expansion. But to reconcile the Hubble tension, some propose that dark energy flared briefly much earlier, just before the cosmic microwave background formed. A short, violent burst of repulsive energy, then gone. If true, it would rewrite the opening chapters of cosmic history. And once again, we find ourselves staring at the same pattern. The deeper we dig, the more the universe refuses to behave like the neat, orderly place we once believed it to be. Not wrong at the edges, wrong at the foundation, and whatever is hiding there is not done surprising us yet. The Casimir effect forces us to confront an unsettling truth. Nothingness is not empty. Even when you strip space of particles, radiation, heat, and matter, it still exerts pressure. It still pushes. It still does things. The vacuum is not a passive backdrop. It is an active participant in reality. And this is where everything starts to feel deeply wrong. Because if empty space can push 2 metal plates together in a laboratory, then, on cosmic scales, that same vacuum energy should be doing something far more dramatic. According to quantum field theory, every point in space should be vibrating with enormous energy. When physicists add up those vibrations, they don't get a small correction. They get a universe-ending catastrophe. Yet the real universe is calm. Galaxies form. Stars burn steadily for billions of years. Space expands gently, not violently. That means something is cancelling out almost all of that vacuum energy with impossible precision, leaving behind just a tiny residue we call dark energy. To cancel something to 120 decimal places is not luck. It is not coincidence. It is either a symmetry so deep we have not yet glimpsed it, or a sign that our understanding of nothing is fundamentally broken. This is why modern physics feels less like a completed structure and more like a building held together by scaffolding. Our equations work astonishingly well in isolation. But when we force them to talk to each other, when quantum mechanics speaks to gravity, they begin to contradict themselves. And that contradiction is everywhere. We see it in the expansion of the universe, accelerating faster than expected. We see it in constants that may not be constant. We see it in galaxies that form too early, stars that are too old, and black holes that grow too fast. We see it in missing antimatter, missing satellites, missing lithium. We see it in muons wobbling just a little too much, as if nudged by an unseen hand. Every one of these anomalies, taken alone, could be brushed aside. An error bar, a calibration issue, a rare outlier. But together, they form a pattern that says the standard model is not wrong, but it is incomplete. It is like discovering that the map you have trusted your entire life is accurate only near the roads you've already traveled. The moment you push into the unknown, the compass spins, the landmarks shift, and the grid lines no longer align. And here is the most unsettling part. Despite all of this confusion, despite all these cracks in the foundations of reality, the universe still works. Atoms still bond. Stars still shine. Chemistry still gives rise to biology. Conscious minds still emerge to ask these questions in the first place, which raises a disturbing possibility. What if the universe doesn't obey a single, clean set of rules? What if the laws of physics we call fundamental are not fundamental at all, but emergent? Local approximations like weather patterns arising from deeper thermodynamic laws. What if gravity, space-time, even quantum fields are not the base layer of reality, but surface phenomena bubbling up from something deeper and stranger? Some physicists suspect this already. They explore ideas where space-time emerges from quantum entanglement, where gravity is not a force, but a statistical effect, where the universe behaves less like a machine and more like a computation or even a phase of matter. If that is true, then many of the paradoxes we see are not bugs. They are symptoms. Symptoms of trying to describe a three-dimensional shadow cast by a higher dimensional object. Symptoms of using classical intuition to understand a reality that was never obligated to be intuitive. And that brings us back to where we started. We built a beautiful picture of the universe. It explained almost everything we could test. It gave us confidence. But now the universe is pushing back. Not loudly, not violently, but persistently, with tiny mismatches, with impossible coincidences, with quiet anomalies that refuse to go away. It is as if reality itself is whispering the same message from every scale. From the smallest particle to the largest structure, you are missing something essential. And the most humbling possibility of all is this: the thing we are missing may not be another particle, another field, or another equation. It may be a completely different way of thinking about what existence actually is. We are not standing at the end of physics. We are standing at the edge of it. And beyond that edge, whatever is waiting has already begun to leave fingerprints on everything we observe. So if the vacuum is powerful enough to squeeze metal plates together in a laboratory, the obvious question becomes unavoidable. Why isn't it tearing the universe apart? Why doesn't this same energy crush galaxies, collapse space-time, or rip reality itself to shreds? The paradox only deepens because this isn't a hypothetical force. We have measured it. We have verified it experimentally. The vacuum is not empty. And yet on cosmic scales, that immense energy seems to vanish without a trace. It is present when we look closely, absent when we look far away. A ghost that only appears when we are standing inches from it. And if even empty space cannot be trusted, then what about matter itself? We tend to think of atoms as eternal. A proton feels permanent, indestructible, born in the first moments after the Big Bang, destined to persist until the heat death of the universe. But many grand unified theories, those ambitious frameworks that attempt to merge all fundamental forces into one, say this comforting assumption is wrong. They predict that protons are not immortal. Given enough time, every proton should decay, breaking apart into lighter particles like positrons and pions. If that is true, then matter itself is temporary, not just stars and planets, But you, the Earth, and the Sun are all slowly evaporating, one proton at a time. To test this unsettling idea, scientists built one of the quietest, most sensitive experiments ever conceived, Super Kamiokande, deep beneath a Japanese mountain, shielded from cosmic radiation, sits a vast tank holding 50,000 tons of ultra-pure water. Its walls are lined with over 11,000 light sensors, all waiting for a single flash. Just one, because if one proton decays inside that water, it should produce a faint burst of light. They have been watching for decades, and they have seen nothing. The result is astonishing. Protons appear to survive for at least 34 years, billions of times longer than the current age of the universe. That sounds reassuring. But for physicists, it is deeply troubling. Many elegant theories predicted proton decay. Nature has so far refused to comply. Either those theories are wrong, or proton decay is so rare that we simply haven't been lucky enough to witness it yet. In either case, the silence is deafening. The proton's stubborn stability is another sign that our attempts to unify the forces of nature are missing something fundamental. And this leads us to the deepest fracture in all of physics, the incompatibility between quantum mechanics and general relativity. We have two rulebooks for reality. General relativity describes gravity as the smooth curvature of space-time, a flexible fabric warped by mass and energy. It works flawlessly for planets, stars, galaxies, and even black holes. Quantum mechanics, on the other hand, tells us that the universe is granular, probabilistic, and jittery at the smallest scales. It governs atoms and subatomic particles with astonishing precision. Both theories are experimentally perfect in their domains, but when you try to combine them, the math collapses into nonsense. Ask a simple question: what is the gravitational field of a single electron? And the equations explode to infinity. Infinity is not an answer. It is physics admitting defeat. This breakdown happens most violently at singularities, like the centers of black holes, where enormous mass is compressed into an unimaginably small space. Relativity demands smooth geometry. Quantum mechanics demands discrete fluctuations. The two clash, and our understanding simply stops. We have tried to bridge this gap. String theory replaces point particles with vibrating loops. Loop quantum gravity weaves space-time into tiny quantized knots. Both approaches are mathematically beautiful. Neither has produced a single testable prediction. We remain trapped, using two incompatible maps for the same territory, unable to describe the core of reality itself. And once we reach that impasse, the questions turn inward, toward the very stage on which physics plays out. Time. You experience time as flowing past behind you, future ahead, present slipping through your fingers. But Einstein's relativity tells us this feeling is an illusion. In relativity, time is just another dimension, woven together with space into a four-dimensional structure called space-time. All moments exist equally. Past, present, and future are laid out together like slices of a loaf of bread. This is the block universe. In this view, the dinosaurs are not gone. They exist on a different slice. The death of the sun is not a possibility. It is already there, waiting on another slice. And if the future already exists, then free will becomes deeply problematic. Are we making choices, or merely moving along a pre-written path? Some physicists hope quantum randomness rescues free will. Others argue that relativity leaves no room for a universal now, and therefore the block must be real. If they are right, then the flow of time is not a property of the universe, it is a trick of human consciousness. As disturbing as that is, it gets worse. Consider the Boltzmann brain. This paradox emerges when you combine thermodynamics with probability. In an eternal universe filled with random fluctuations, it is vastly more likely for a single brain to spontaneously assemble, complete with false memories, than for an entire universe with galaxies, stars, and a real history to form. Statistically, lone brains hallucinating reality should vastly outnumber genuine observers like us. If our theories predict that, then our theories are wrong. We call this the measure problem. We must explain why the universe favors rich, structured histories over isolated flashes of consciousness. So far, the math offers no comfort. According to probability alone, reality itself is the unlikely option. If these philosophical horrors feel too abstract, physicists have tried to ground the problem by looking for something concrete limits. If reality is simulated, or if it runs on deeper informational rules, it should have constraints. And, intriguingly, it does. High-energy cosmic rays obey a strict speed limit known as the GZK cutoff, around 5 × 10^19 electron volts. Particles above this energy should collide with background radiation and slow down. As if the universe enforces a hard cap, space itself has a minimum resolution, the Planck length, about 6 × 10^-35 meters. Below this scale, the concept of distance loses meaning. Why does reality have pixels? Even stranger, certain mathematical structures found in advanced theoretical physics resemble error-correcting codes, the same kind used in digital communication systems. This does not prove we live in a simulation, but it does make the universe look less like a chaotic wilderness and more like a system with built-in constraints, optimizations, and safeguards. And if all of that weren't unsettling enough, physics has identified a way the universe could end instantly, without warning. The Higgs field, which gives particles mass, may not be in its lowest possible energy state. We could be living in a false vacuum, a metastable condition that feels stable but isn't. Through quantum tunneling, a bubble of true vacuum could spontaneously form anywhere. Inside it, the laws of physics would change. Atoms would cease to exist. Chemistry would fail. The bubble would expand at the speed of light, erasing everything it touched. No warning, no escape. One moment existence. The next moment, deletion. Some calculations suggest we are safe for billions of years. Others hint that the cliff edge may be closer than we think. Either way, the message is the same. Reality is not as solid as it feels. The ground beneath our feet is mathematical, probabilistic, and possibly temporary. And perhaps that is the final, most unsettling lesson of all. The universe is not a finished story. It is not a solved equation. It is a fragile arrangement balanced on unknown principles. We exist not because reality is stable, but because for now, it has not yet failed. Things can influence each other instantly across vast distances. Causes don't always precede effects in the way our intuition demands. Reality, at its deepest level, already behaves in ways that feel less like a story and more like a paradox. So perhaps the discomfort we feel now is not a failure of science, but a collision between human intuition and the true architecture of the cosmos. We evolved to throw spears, recognize faces, and survive one afternoon at a time. We did not evolve to comprehend vacuum fluctuations, non-local entanglement, or universes that may reboot themselves after trillions of years. And yet, here we are, trying anyway. The unsettling possibility is this: the universe may not be obligated to make sense to us. Logic, causality, and even mathematics might be emergent tools, useful approximations that work locally, but fracture when pushed to cosmic extremes. Just as Newton's laws collapse near the speed of light, our deepest assumptions may collapse when confronted with the full scale of reality. Quantum mechanics already forces us to accept that particles can exist in superpositions, that observation alters outcomes. That probability replaces certainty at the foundation of existence. Entangled particles remain connected regardless of distance, mocking the idea that space is a meaningful barrier. These are not small quirks. They are hints that the universe operates on principles profoundly alien to everyday reasoning. When we combine this with Gödel's incompleteness, the proof that no logical system can fully explain itself, we arrive at a deeply humbling conclusion. Even if we write down a theory of everything, it may still leave truths forever out of reach, not hidden by distance or energy, but inaccessible in principle. There may be facts about reality that are true, real, and active, yet forever unprovable from within the system we inhabit. If that is the case, then anomalies like the cold spot, the Hubble tension, vacuum energy, and dark matter are not bugs in the code. They are boundary markers, places where our intellectual tools reach their limits, places where reality stops answering questions in a language we understand. And that reframes everything. The growing list of cosmic contradictions is not evidence that science has failed. It is evidence that science is doing exactly what it is meant to do, push until something breaks. Confusion is not ignorance, it is progress at the edge. We are no longer wrong in small ways. We are wrong in fundamental ways. And that is how revolutions begin. Every great shift in understanding started this way. Epicycles piled up until Copernicus removed Earth from the center. Mercury's orbit refused to behave until space-time itself was bent. Ultraviolet catastrophes shattered classical physics and gave birth to quantum theory. Each time, reality didn't change. Our story about it did. We are standing at another such threshold. The universe we thought was orderly now looks unstable. The constants we trusted may drift. The vacuum we called empty seethes with hidden energy. Time may not flow. Space may not be smooth. Matter itself may be an accident. And existence could end without warning or repeat forever in cycles beyond memory. Yet despite all of this, the universe is not hostile to understanding. It is simply indifferent to comfort. It reveals itself in fragments, through anomalies and contradictions, daring us to let go of old frameworks and imagine something radically new. And perhaps that is the final lesson hidden inside all this cosmic confusion. Not that the universe is broken, but that our picture of it is incomplete. Not that nothing makes sense anymore, but that sense itself is evolving. We are explorers at the edge of comprehension, staring into a reality that is deeper, stranger, and more profound than any story we have ever told. And the fact that we can even glimpse these cracks, that we can ask these questions at all, is not a failure. It is the clearest sign yet that we are closer than ever to something truly transformative. Because when the universe stops making sense, that is usually the moment just before it reveals a deeper truth. A cat can be alive and dead at the same time. That strangeness isn't a bug in the system. It's a feature. Maybe the problem isn't that the universe refuses to make sense. Maybe the problem is that we are trying to force a non-linear, multi-dimensional reality into a neat, linear, three-act story with a beginning, a middle, and an end. We are trying to read a novel written in a language that has no alphabet. Anomalies like the cold spot or the axis of evil may not be errors at all. They may simply be the moments where our translation software fails, where human intuition breaks under the weight of something far larger and stranger. And if that's true, then mystery isn't something to be eliminated. Mystery is the point. The fear we feel when we stare into the great void, or contemplate false vacuum decay, is not just fear of the unknown. It's vertigo, the dizziness that comes from realizing how small we are, and how vast the universe truly is. And the universe is under no obligation to follow our rules. We live on a small rock, orbiting a very average star in the suburbs of an ordinary spiral galaxy. We've built a small island of light and called it science, to keep the darkness at bay. And it works. It keeps the lights on. It keeps planes in the air. It keeps the world running. But every time we point a telescope into the dark, we're reminded just how tiny that island really is, and how infinite the ocean surrounding it has always been. We've seen that the history of the universe is darker and stranger than we imagined. We've seen that our sense of safety is an illusion, maintained by delicate energy fields balanced on a knife's edge. We've seen that we may be alone, Or worse, we may be silent in a forest full of hunters. The next time you look up at the night sky, don't just see the stars. Look at the black space between them. That's where dark matter flows. That's where vacuum energy seethes. That's where signals from long-dead civilizations may be passing through you right now. We are drifting in the dark. We don't have a map. The clock is broken. The compass is spinning. And the only thing we know for certain is that the deeper we look, the less sense everything makes. And honestly, I wouldn't have it any other way. Because a universe that makes sense is a small universe. A universe that unsettles us, that frightens us, that humbles us, that is a universe worth exploring. Sleep well. If you enjoyed this descent into the impossible, make sure to subscribe. It won't save you from vacuum decay, but it will help the algorithm. I want to know which of these mysteries keeps you awake at night. The dark forest simulation theory, or the idea that the universe itself might be fundamentally broken. Let me know in the comments below. And if you want to go even deeper into the things that should not exist, check out the playlist right here. Thanks for watching, and I'll see you in the next one, assuming the universe is still here.